These are notes from Elham's Math 70 from Monday, April the 27th, section 12.2, page 705. Today we'll be doing something called permutations and combinations. And we'll start off by introducing the factorial function. So factorials apply to whole numbers, and we put an exclamation point after that. So when you see 0 and an exclamation point, we say 0 factorial or 1 factorial or 2 factorial and so on. All right, so 0 factorial is 1 by definition. It's basically 1 because we said so, but it's actually a very good definition. A lot of the math formulas work out very nicely if 0 factorial is equal to 1. 1 factorial is also 1 by definition, so not very interesting so far. But it starts getting interesting with 2. So 2 factorial is defined to be 1 times 2, which is 2. 3 factorial is 1 times 2 times 3, which is 6. 4 factorial is 1 times 2 times 3 times 4, which comes out to be 24. So basically, for a whole number factorial, you multiply 1 times 2 times so on, and you keep going until you reach the number that you're looking for the factorial. In this case, 4 factorial is 1 times 2 times 3 times 4. I'm writing this also because obviously you could also start at the top. You could start with 4 times 3 times 2 times 1. All right, then we have something called permutations. A permutation of n objects selecting k at a time. The formula for that, written as Pn comma k, Pnk, is defined to be n factorial divided by n minus k in parentheses factorial. Essentially, for a permutation, order is important. The order in which you select something is important. And then there's a formula for combinations. For a combination of n objects selecting k at a time, notice the language is very similar to permutation, only it's a combination. So instead of a p, we put Cnk. It's defined to be n factorial divided by k factorial divided by n minus k factorial. In this instance, order is not important. So for permutations, an order is important. Combinations, order is not important. So here's some examples from the homework. Problem 1 asks you to compute 8 factorial. By definition, it's 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. Punch it in your calculator, 40,320. And notice, of course, you could have started at the top, and later on I'll start at the top. 8 factorial, you could have also gone 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Same thing. Number 3 asks for 9 factorial minus 5 factorial, so you just work them out separately. 9 factorial is this, 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9. Minus 5 factorial means 1 times 2 times 3 times 4 times 5. So 9 factorial, punch it in the calculator, it's this. 5 factorial is this. Subtract 362,760. Now we're actually going to figure out permutations or combinations. P85, okay, on a grander scale, it's a permutation of 8 objects taking 5 at a time, but by definition, it's 8 factorial divided by 8 minus 5 factorial. 8 minus 5 factorial is 3 factorial. This computation is so easy, normally we'll just go straight to it, and I'll show you what I mean when we get over here. All right, so 8 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8, divided by 3 factorial, 1 times 2 times 3. Notice for a lot of these computations, you get a cancellation. The 1, 2, and 3 can cancel this 1, 2, and 3. So you're just left with 4 times 5 times 6 times 7 times 8, which is 6720. So the answer is 6720. On a deeper scale, if you want a permutation of 8 objects taking 5 at a time, that would be, for instance, suppose you have 8 people, and then you're picking 5, where the first one is president, second one is vice president, third one is secretary, fourth one is treasurer, and fifth one is some other office. And so you have 8 ways to choose the first person. That's 8. Okay, times 7. Once the first person is picked, there's only 7 left. Okay, and then times 6 after that, and then times 5 and times 4. So the number of different permutations you can have of president, vice president, secretary, treasurer, and elector, or something like that, is, well, you have 8 ways to choose the first person, times 7 for the second, because once you choose the first person, there's only 7 left, and then 6, and then 5, and then 4. Okay, so that means that's a permutation of 8 objects taking 5 at a time. So an example would be 8 people. How many ways can you pick 5 people, 1 to be president, vice president, secretary, treasurer, and elector, or something like that. Okay, here's 11. P80, by definition, is 8 factorial over 8 minus 0 factorial. Well, that's 8 factorial divided by 8 factorial. I don't have to compute that, but that's basically 1. Okay, on a deeper scale, that means if you have 8 objects, how many ways can I choose 0 of them? Well, there's only one way. You just don't pick any of them, and there's only one way to do that. 17 gets more complicated. P60 over P66. So this is 6 factorial divided by 6 minus 0 factorial. This is 6 factorial divided by 6 minus 6 factorial by definition. Okay, well, this is just 6 factorial divided by 6 factorial. That's 1. The bottom is 0 factorial, which by definition is also 1, so you can ignore that. It's basically 1 over 6 factorial, which is 720. So the answer is 720. Again, on a deeper scale, P60, it's sort of like this one. You have 6 objects. How many ways can I choose? None of them. Well, there's one way. Just don't pick any of them. P66 means you have 6 objects. How many ways can I pick 6 of them in order? Well, there's 6 factorial because there's 6 ways to choose the first one object. Then after that one is chosen, there's 5 more, so it's times 5. Then after that, it's 4 more, times 3, times 2, times 1, so it's 6 factorial, or 720. Okay, starting with 19, we have something called combinations. It's a little bit different. There's a different formula. So for combinations, order is not important. So I'll be using this formula now, n factorial divided by k factorial, n minus k factorial. So C92 is 9 factorial divided by 2 factorial, 9 minus 2 factorial, which is 7 factorial. So normally I'll go straight to that shortcut. 9 minus 2 is no big deal. We all know 9 minus 2 is 7. So here's 9 factorial written out. 2 factorial is 2 times 1. 7 factorial is 7, 6, 5, 4, 3, 2, 1. Notice, to save computations, the 7, 6, 5, 4, 3, 2, 1 cancels the 7, 6, 5, 4, 3, 2, 1 there. So you just have 9 times 8 divided by 2. That's 9 times 4, which is 36. So this is a combination of 9 objects taking 2 at a time. Just mention quickly about the significance of that. If this were a permutation, P92, that would be, for instance, you have 9 people. How many ways can I choose a president and a vice president? Well, there's 9 ways you can choose the president, and then after that person is chosen, assuming the president can't also be the vice president, there are 2 ways you can pick the vice president, so that would be 9 times 8, which is 72. Now, how do we get 36? 72 divided by 2. That's where, if you're just taking 2 people, and order is not important. Okay, so if I have 9 people, I'm just selecting 2. So I just say, okay, I need 2 of you to help me with the job. It doesn't matter if I pick person A and then person B, or person B and then person A. It doesn't make any difference. Okay, now for permutations, P92, it does make a difference if Mary is president and John is vice president, or vice versa. That's going to be a different permutation. But if I just simply say there's 9 people and I just say, okay, Mary and John, you come with me to do a job, it doesn't matter if I say Mary, John, or John, Mary. Order is not important, so I'm dividing the total number of permutations, in this case, by 2, so there's only 36 combinations of what I would have here. Okay, 23, just more of the same game. C62 times C73. C62 is 6 factorial over 2 factorial, 4 factorial. Yes, that's 6 minus 2, but we know 6 minus 2 is 4. Then 7, 3, combination 7, 3, 7 factorial over 3 factorial. 7 minus 3 factorial is 4 factorial. Okay, 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is 1 times 2. 4 factorial is 4 times 3 times 2 times 1. Notice very conveniently the 4, 3, 2, 1s cancel the 4, 3, 2, 1s here. 7 factorial is 7 times 6, 5, 4, 3, 2, 1. 3 factorial, 3 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1. Notice the 4, 3, 2, 1s can cancel 4, 3, 2, 1. So here I have 6 times 5 divided by 2. 7 times 6 times 5 divided by 3 times 2 is 6. Notice that 6 can cancel that 6. And here 6 divided by 2 is 3. So I have 3 times 5 times 7 times 5, and that comes out to be 525. Then for 27, C97 times C53 divided by C 1410. So this is 9 factorial over 7 factorial 2 factorial, 5 factorial over 3 factorial 2 factorial, by formula it's 5 minus 3, 14 factorial over 10 factorial 4 factorial. Alright, so I wrote it all out, 9 times 8 times 7, blah blah blah, down to 1, 7, 6, 5, 4 down to 1, 2 times 1, very conveniently 7, 6, 5, 4, 3, 2, 1, cancel 7, 6, 5, 4, 3, 2, 1. So now I have 9 times 8 divided by 2 over here. Here 5 factorial means 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. I can cancel 3 times 2 times 1, 3 times 2 times 1. So I have 5 times 4 divided by 2. And then 4 factorial is all this mess. 10 factorial is all of this. 4 factorial is this. Notice I can cancel 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 with 10, 9, 8, 7 all the way down to 1 here. So I'm left with 14, 13, 12, 11 times 4 times 3 times 2. And I have some extra cancellation now. 8 divided by 2 is 4 in green here. 4 divided by 2 is 2 here. So on top I now have 9 times 4 times 5 times 2. And on the bottom, this 4 times 3 right there is 12. So I pick these two, 4 times 3, to cancel with that 12. So that cancels that. And then that 2 can cancel that 14, leaving with a 7. So I have 7, 11, and 13 on the bottom. And multiply it all, you have 360 over 1001 is the answer to 27. Alright, so these are notes for Milham's Math 70, Monday, April the 27th, section 12.2, page 705.